Today, we are very happy to deliver the second Tan Swan Beng public lecture. The school is very proud to be able to invite Professor Delwyn Fredlund to give a lecture on application of unsaturated soil mechanics for environmental protection and sustainability. Professor Fredlund is internationally renowned for his research on the behavior of unsaturated soils and has a great impact on the livability of cities. This is an issue of growing significance worldwide, particularly to a rapidly aging city-state like Singapore. So finally, I wish all of you a very, very fruitful session today. Thank you very much.
Okay. Good morning again. My name is Delwyn G. I shall be the MC for the following deliveries. Before we invite Professor Fredlund to deliver the Tan Swan Beng public lecture, I'd just like to briefly introduce Professor Fredlund. I think if we need to go through all his accomplishments, it will take longer than his probably lecture itself. So I'll just give you a summary of Professor Fredlund's achievements. Professor Fredlund has spent over 40 years conducting research into the behavior of unsaturated and expansive soils. His research studies have involved all areas of unsaturated soil behavior, ranging from the flow of water and air through unsaturated soils to the shear strength and volume change of unsaturated soils. Most of his career is actually spent at the University of Saskatchewan, Saskatoon, where he actually organized the unsaturated soil groups for conducting research on unsaturated soils. This has led to him supervising over 75 MSc and PhD graduate students while he's still at the university. Since then, he's now presently heading the Golder Unsaturated Soil Groups, linking the worldwide offices of Golder Associates, solving problems on unsaturated soils. Among his numerous awards, Professor Fredlund has received the Zagi Award in 2005 given by ASCE, Order of Canada 2004 from the Federal Government of Canada for a significant contribution to Canada and other countries around the world. Julian Smith Award for Lifelong Contribution to Engineering Profession in Canada in 2009. Prime of Life Achievement Award, University of Saskatchewan in 2011. Professor Fredlund has made his life mission to bring unsaturated soil mechanics into routine geotechnical engineering practice. And we are very privileged today to have Professor Fredlund as the endowed Tan Swan Beng professor. So can we give a warm welcome to Professor Fredlund to deliver his Tan Swan Beng lecture.
Thank you, Professor Leong, for your kind introduction. I want to start by saying I count it a real honor and a privilege to be able to be here today and to present the Tan Swan Beng lecture. And I also would say thank you for organizing this day in March when it's minus 30 to minus 40 in my city, so I could come to Singapore and enjoy your wonderful climate here. I feel that it is important that we remember and that we pay respects to the outstanding engineer who contributed so much by way of engineering in Singapore. And of course I am referring to engineer Tan Swan Beng. I have read about his achievements, and I have put into my own words, summarized some of his contributions, and I would like to go through those. Tan Swan Beng was an engineer with a passion for engineering, for excellence, innovation, and a champion for technology application. Swan Beng was an engineer of great distinction who reached the pinnacle of the engineering profession in Singapore and remained there for many years. Swan Beng was an engineer with strong convictions, a sharp mind, and a deep passion for civil engineering. Swan Beng was a specialist in geotechnical engineering, drafting the code of practice for foundations in Singapore. Swan Beng joined the Public Works Department in 1968 and became Director General in 1985, where he remained until the time of his passing. And I trust that these few words will once again remind us of the outstanding contribution that he has made to engineering. Let me introduce my lecture today in the form of a question. What does unsaturated soil mechanics have to do with environmental protection and sustainability? There are a couple of words in the title that we hear a lot. We call them buzzwords, but they happen to mean different things to different people. And so I think it is important that we define some of the terms that we're talking about, and I will try to do that. I will then go back to the origins of soil mechanics and ask the question, what really did we learn about soil mechanics in the early days, the early years, the 1940s? Terzaghi soil mechanics, what was it? What did it teach us? And then I will point out the things that it did not teach us, some very important things that we need to meet the conditions for sustainability and the protection of our environment. And I will take a few examples from engineering, and I will try to illustrate the things that we can do now that we could not do previously because we embrace unsaturated soil mechanics. And I'll use the concept of contrasting coefficients of permeability, putting two materials side by side that have highly contrasting permeabilities. And then I will conclude with the need to consider the concepts of environmental protection and sustainability in order to meet some of the challenges that we face. Let us define the word sustainability. It comes from the Latin word sustenere, which means to maintain and endure. You know, in the 1980s, there was a buzzword that we heard a lot about, and it was environmental protection. It came out mainly out of studies out of the United Nations. And it was necessary for countries to develop environmental treaties. And it applied to both developing countries and developed countries. Developed countries wouldn't work with developing countries unless they had an environmental treaty in place. But within about 10 years' time, there was a new buzzword that came on the scene, and it is the word sustainable development. And it was also promoted and pushed by the United Nations. What does it mean? Sustainable development means meeting the needs of the present without compromising the ability of future generations to meet their needs. The 2005 World Summit on Social Development recognized sustainability as having three pillars. It was a reconciliation between those three pillars, the one pillar being environmental protection, the other demands that society has, they want them met, and the third was economic growth. It is not easy to bring these three pillars together. In fact, the environmentalist would probably look at this and say that this is a bit of an oxymoron. In other words, it's an impossibility, because as soon as you do something and as soon as you change something, to them, you have hurt the environment. Well, if we adopt that kind of a definition, we won't get very far. Let's say that a more acceptable definition is what I have up at the top here. It is improving the quality of human life while living within the carrying capacity of supporting ecosystems. And I would like to just change that a little bit for the audience today, because we are dealing with geotechnical engineering primarily. And I would say we can describe it this way. It is responsible and proactive decision-making along with innovation that minimizes negative impact and maintains a balance between social demands, environmental protection, and economic growth. Now I want you to come back with me to the 1940s, when we had what we call historical or classic soil mechanics. Really, it was a saturated soil mechanics, which was being put together as a science and being taught in our universities. What were the key things that we were learning in the early days about soil mechanics and that stayed with us for so many years? And then, what were the limitations of what we had been taught? What important role could the physics of unsaturated soils bring to the table? And we were not considering it because we were just dealing with saturated soils. We have now found that in our thinking we have to go through a considerable change in how we think about soil mechanics, how we think about unsaturated soil mechanics. In fact, it may even be called a paradigm shift, because we have to do things so differently than we used to, and we have to think differently as well, especially when we want to take advantage of unsaturated soil mechanics and try to embrace environmental protection and sustainability. It was 1943 when Karl Terzaghi wrote the book, Theoretical Soil Mechanics. He wanted to make soil mechanics a science, and he could do it because of one main thing. He discovered that all saturated soil behavior was controlled by a stress state variable. He called it effective stress. Effective stress was the same in Singapore as it was in Canada. In fact, it covered all countries of the world. We had a common pivotal point to which to focus all things that we experienced with soils. We could relate it to changes in effective stress. And because we had effective stress, we had a science. Soil mechanics is a science because we know the stress state. Now, Terzaghi did not try to focus on all of the problems with saturated soil. He really picked three primary problems: the flow of water through porous media, the shear strength of soils and its application to bearing capacity, slope stability, and so on, and the volume change behavior. If you look at his textbook and the challenge that he had to put that book together in 1943, we can ask ourselves, what was he really trying to do? He was attempting to make soil mechanics a science with closed-form solutions for simplified representations of geotechnical problems. He would take complex problems and he says, what's the simplest model we can create so that we can think the way the soil behaves? And then on an 8.5 or sheet of paper, do some calculations and come up with a solution. This is what he did, and he really focused only on saturated soil behavior. Let's just look at a couple of the difficulties encountered in that. With working with Arthur Casagrande, he put together these classic pictures of flow nets. I've drawn a line across them halfway down here because I've separated them. There's two classes of problems. There's confined flow, and there is unconfined flow down here. What's the difference between confined flow and unconfined? And do we have these today? We don't usually teach our students about confined flow and unconfined. Unconfined flow meant I do not know the boundary conditions on my problem, and so I will make an empirical guess, and now I'll try to solve a different problem. We don't do that today. We take this problem and we look at it quite differently. We do not need to have a separation line between the saturated and the unsaturated, but he had to have that. So what was missing in the way he was looking at seepage problems? He could consider only the saturated zone of the problem. The actual boundary condition is the ground surface up here. He could not consider it. He could not consider the effect of rainfall on the stability of a dam. Could not consider the effect of drying. No moisture flux boundary conditions could be solved. And the dividing line between the saturated and the unsaturated was an empirical line, which he may be able to get for this problem, but the next problem he would have another problem. When it came to slope stability, there was some serious limitation. He just looked at simple slopes, simple geometries. One slope angle, one shear strength described by the undrained shear strength. If you don't describe your problem in terms of effective shear strength parameters, you cannot take into account the change in pore water pressures. You know that the thing that is changing with time that creates instability is always pore water pressures. This is a serious limitation. But we had one other class of problems related to unsaturated, related to saturated clays, and that was the consolidation theory of a clay layer. If a load is applied to it, we could predict the rate of volume change and the dissipation of pore water pressures. This was the pinnacle of all analysis that we could do in saturated soil mechanics. And this was the analysis we taught our engineers how to do this, because it taught them how to think the way the soil behaves. And we were very important people, because now we were predicting the future. We could predict the amount of volume change, the amount of settlement, the distortion to building, and so on. Now I want to just summarize our time span from the 1940s to the present. And I want to put them into several eras. From the 1930s to the 1960s, I call it the era when we were searching for closed-form solutions. Yes, some of them were graphical, some of them were simple integration, but basically they were closed-form solutions to simplified problems. In the 1960s, we came across this very valuable tool called the computer. What did we do? We sat down and we took our old problems that we had solved on a piece of paper and said, can we use the computer to solve them? And so for about 30 years, we became familiar with the computer. We got used to the hardware and the software, and we solved those problems. But it was about this time that we realized, you know, this computer has the potential for looking at our problems in a very different way. We can now go back to our soil mechanics problems, and we can find new ways to analyze the old problems. And that's why I put this as a very important error here. It's the generation of numerical modeling. We can now embrace both the saturated soil part and the unsaturated soil part and into a single unit, analyze them at the same time. We also realize our world has a moisture flux boundary condition, and we can quantify it. So we can have moisture flux boundary conditions. This opens geotechnical engineering to a wide range of new problems that can be solved that could not be solved previously. At the top of this slide, I identify the two major omissions from classic historical saturated soil mechanics. The moisture, both temperature and moisture flux boundary conditions, were omitted. The physics of unsaturated soil behavior was not provided. And so, if this is our world, here's the ground surface. Above it we have the atmosphere and our climate that imposes rainfall, and evaporation goes up. And down below the phreatic line we have the saturated soil. But in between we have a very important zone called the unsaturated soils mechanics zone. Why is it so important? Because this is the zone that it is like a sponge. It has the ability to absorb water and to release water. It has the ability to transmit water through it at varying rates, depending upon the stress state in this. We can contaminate our world at the ground surface, but it must get through this zone. So for many of our problems related to contaminant transport and environmental engineering, this becomes the key zone. Without unsaturated soil mechanics, we cannot deal with that. And I just point out up here, when you look at environmental protection and sustainability, this becomes a crucial zone because we contaminate our world, as I mentioned there. So that ground surface, let me just focus on it for a minute. We have precipitation that comes down. We have weather stations that record the amount and the rate at which that water comes down. Some of it will run off. Some of it will evaporate, go back to the atmosphere. Some of it will infiltrate. These are independent entities which must be evaluated. And if they can be evaluated, we can get the infiltration at the ground surface. If this were a cover system now, we could model and see what comes through the cover system. This would be called deep percolation. How much flows laterally? So the modeling of near ground surface conditions always requires an understanding of unsaturated soil mechanics. Let me put it another way to try to illustrate what are some of the differences between saturated soil mechanics and unsaturated soil mechanics. The saturated soil mechanics that Terzaghi gave us and others, it was a soil mechanics of constants. We could take and describe the strength of the soil in terms of Moore-Coulomb. We had an intercept and a friction angle. For seepage problems, we had a coefficient of permeability. For consolidation, we had coefficient of consolidation. We always tried to have just constants, one value for our soil properties. We went to the field, we took undisturbed samples, and we measured these soil properties. And then we did analysis. And the analysis were easy because we ended up with a linear soil mechanics. Now what happens when we try to embrace unsaturated soil mechanics over on this side? Our soil properties are no longer constants. They all become functions of the negative pore water pressure, the distance from the water table, or the suction in the soil. So they are no longer constants. Now they are functions, nonlinear functions. How are we ever going to measure these properties? Well, we don't even try because it is too expensive. It is too costly. We have, though, gone through a paradigm shift in our thinking, and we have come up with a solution. We say we cannot measure these properties, which are now functions. It's too costly, so I will measure something else. And that something else is called the soil water characteristic curve. This term, soil water characteristic curve, becomes the key to the implementation of unsaturated soil mechanics, because if I know this relationship for soil water characteristic curve, I can now estimate, rather than measure, I estimate all of my unsaturated soil property functions. I have a little bit of a problem in that soil mechanics becomes nonlinear. When we say that it becomes nonlinear, it means you cannot go through the calculations one time and get an answer. You must try, estimate, try to get an answer, refine it, go over and over, maybe 100, 150 times, We can't do that longhand. We needed Bill Gates to come along with the digital computer. And so at the same time that the computer is emerging in the world, so is unsaturated soil mechanics exploding. And the two fit together very well. But we have had to change our thinking. We have now realized that our problems need to be put into a different context. Every problem that I am aware of in unsaturated soil mechanics can be formulated within the same framework called a boundary value problem. These are the characteristics. I'm not going to spend that much time on boundary value problems, just enough so that you know what we're talking about. The first thing was defined is the geometry and the stratigraphy, the ground surface profile and the soil layers. What are the properties? Well, the main property that we're going to have to define is the soil water characteristic curve, because then I can get the permeability function. Then I can get the water storage function. I'm going to need to know the boundary conditions. You cannot solve a problem without boundary conditions. And I'm going to need to use the climate information to help me get a moisture flux, because so many of our problems are driven by changes in moisture flux at the ground surface. If you look at a slope that's been excavated and you say, is it stable? And it's sitting there, it is stable. What would make it unstable? Changes in the suction in the soil, infiltration of moisture. The fourth component is the formulation that embraces both the physics of saturated and unsaturated soil behavior. So there's a theory part here. And that theory would always lead us to the development of a partial differential equation that we don't like. So we will put it in a black box, and we call it our partial differential equation solver. And we go to the websites, and we pull off the website partial differential equation solvers. We put that into the partial differential equation solver into a box. Now we can use that box and we can play games the same way as our children do on the computer. We can do design games. We can try it. If we have these conditions, what will happen? I wonder what will happen if we change something. What if? That's what a lot of our design becomes. So these are the components. And I don't care if you're looking at airflow through soils, if you're looking at chemicals through soils, water flow through soils, water vapor, whatever it might be, all of those problems will be solved within the context of a boundary value problem. Just to make it drive it home a little more, here's a simple slope, a geometry like this, and I call this a boundary, I make this a boundary, all of these boundaries, because the world is too big to solve all the world's problems, so we put boundaries and say, I'll just solve this. And this little element here is called a representative elemental volume. If I can describe the physics of that one element, then I can solve it for more and more elements, finite elements, all the way around here. So the physics will always take the form of a partial differential equation. And I'm only going to show you this one equation so that you know what I mean by a partial differential equation. This has the change in head with respect to space in the x direction and the y. It's an equation that describes the flow of water through a saturated soil, through an unsaturated soil. It's the same partial differential equation now, except for unsaturated soils, it will be nonlinear because our properties will be a function of soil suction. But with the computer, we can still solve these. I want to just take a minute so we get a little better understanding of what's meant by the soil water characteristic curve. On the top up here, I put volumetric water content versus the logarithm of suction. I say for a coarse-grained soil, we have this red line. For a fine-grained soil, we may have a line that looks like this. And where this line breaks and curves here is called the air entry value. It's the point at which the tension in the soil, at which the soil starts to desaturate. And as it desaturates, it goes like this. We can use these equations along with the saturated coefficient of permeability to estimate or calculate the permeability for a coarse-grained soil, for a fine-grained soil. We don't go into the lab and measure the permeability functions. It is too costly. We estimate them. And other professions that are related to ours are doing exactly the same thing. Now, if I were to ask you, which soil is more pervious? Which one will handle more water flow? The coarse soil or the fine soil? I wonder what you would say. I won't ask you to vote. But if you say, oh, the coarse-grained soil, it will allow the most water to go through. But I would say it all depends on what the state of stress is. If I have a low suction represented by this vertical line, then this coarse grain, red one here, it will be the highest permeability. But if I just happen to have a suction on it out here, and I go down to my permeability functions, now I find that the fine-grained soil has a higher permeability than the coarse-grained. That is one of the first lessons we have to learn, that a coarse-grained soil can be impervious. It can create a capillary barrier, and we can take advantage of those characteristics. There is no one permeability for this coarse-grained soil. It may vary over 5 to 10 orders of magnitude. The fine one may vary over less. And we need to have equipment to measure that soil water characteristic curve. And the devices are called the pressure plate devices. And you will see more information on that in Professor Harjo's talk later. But basically, it's like our consolidation cell now that allows you to control air pressure, water pressure, and total stresses. It's like a consolidometer, which is a little bit more elaborate than what we are familiar with. So let's supposing now we have a solver that can solve that partial differential equation that I showed you for this case of this dam. We divide it up into elements called finite elements. Really, we don't care about those finite elements anymore because they are part of the mathematical solution. This is what we want down here. We want to know that if I put this head against the dam, how will it dissipate through the clay core and through the rest of the dam? And this is our solution. The mesh is now part of the mathematics. And so in the 1970s, I started to think about putting together a textbook, synthesizing the information on unsaturated soil mechanics. And I realized I did not have time to put it all together, but I did happen to have a very brilliant graduate student who said, I will help you. And so this is what began a long journey together. I realized in the 1970s, as after I completed my PhD degree, that for unsaturated soil mechanics, we had the key to describing the stress state. We now had net total stress and matrix suction in the soil. We now had a soil mechanics with 2 independent stress state variables. You know, that's what made saturated soil mechanics a science, was because they knew the stress state. I said, we know the stress state for an unsaturated soil, so we can put together a science. And so we set out to put together a science for unsaturated soil mechanics, and we realized we had a problem. The problem was that our way in which we looked at the problems of soil mechanics had changed. Remember how I described what Terzaghi put together? It was an attempt to make unsaturated soil mechanics a science through the use of boundary value representations of complex saturated and unsaturated soil problems. No more closed form solutions. The computers had influenced how the science was going to be presented and how it was going to be practiced. This book was published then in 1993. Why in the world would we publish another book? The book published in 1993 attempted to lay out the theory, to understand the behavior of unsaturated soil mechanics. What we realized, though, is that engineers out in practice needed some help. There was still a big step from the theory to how to solve practical problems. Somebody needed to take and help them, take them by the hand and show them how to apply the theory to the first problem, and after that, they can go on their own. And so that is why this one is called Unsaturated Soil Mechanics in Engineering Practice. It also ended up being about twice as long as the first book. It's almost 1,000 pages, and I can tell you it'll probably be the last book I ever write in my life. But the attempt is to try to do a better job of helping engineers protect the environment and to promote sustainability by saying there is benefit in using unsaturated soil mechanics. You know, I don't, when I teach unsaturated soil mechanics, I'm not trying to teach them another partial differential equation. I hated those things when I was a student, and I still don't think we need to focus on them. Rather, we need to teach our students to think right. If you learn to think the way the unsaturated soil behaves, only then can we take advantage of the unusual behaviors of unsaturated soil mechanics. So now I view my job as more brainwashing. Brainwashing the students to think right. Then you will make the right kinds of decisions. Now I want to take you through a couple of examples, and I'm going to use the concept of contrasting permeabilities to help you try to see the dramatic difference between saturated and unsaturated soils type problems. We need to understand the physics of unsaturated flow. I'll use the flow example. And we need to take advantage of varying permeabilities. Some of the examples. I'll just look at a column of soil that's got partly fines and partly coarse. I'll look at a dam with a clay core, a dam with a chimney drain. See, there's two types of dams that have been built in the world. There's those dams that we built where we put a clay core to cut off the flow. And then there's those dams where we put the very pervious material in the middle of the dam. Two kinds. And I'll just show that basically they do the same thing because they have contrasting coefficients of permeability. And then we will get finally to the slope and try to apply it to slope stability. Well, here's the column I was referring to. This is a column built by a graduate student. And down the very middle of this column is a barrier. Well, it's not really a barrier. The way it was built, we started at the bottom. We filled half of it with fines, and then half of it with coarse, half of it with coarse and fines. And so right up the middle is the dividing line between the fine and coarse material. The fine material, we measured its soil water characteristic curve, predicted the permeability function. We did this for the coarse as well. You can see the coarse is about an order of magnitude more pervious when it's saturated. And so now we're going to put water in at the top. We're going to sprinkle water at the top. And I'll ask you the question, if you put water sprinkled evenly across the top up here, will it flow down the fine part or will it flow down the coarse part? Well, the first example we look at is a case where the applied flux at the ground surface is low. It's a relatively small value. It's slightly below the permeability for the fine material. Now, I'll try to help you see what happens here. We evenly sprinkle it across the top. Very quickly, the water flows from the coarse over to the fine, goes down the fine layer until it comes to the bottom, and then it starts to come out all across the bottom here. But this is the important part I enlarge over here, so try to make it clear. Why would the water go from the coarse over to the fine material and flow down the fine? Why? Because the coefficient of permeability of the fine was higher under this negative pressure, was higher than the permeability in the coarse. Now I'll take that same soil and I'll apply a higher moisture flux at the ground surface. It'll be above the permeability for the fine material. And as I sprinkle it evenly across the top, evenly across the top, you'll see now the water wants to come down the coarse material here. So the answer is Will it flow down the fine or the coarse? It depends on what the flux is at the ground surface, because that flux at infiltration under a gradient of 1 will decide which side is most permeable, and the water will flow back and forth depending upon which is most permeable. Now there's an example problem that puzzled Terzaghi. How do I know it puzzled Terzaghi? Because in 1930s he wrote in Engineers' News Record about the cross-section of a dam with a clay core, and he noticed that the water would siphon over top of the clay core. This puzzled him. Why would water flow uphill over top of this clay core? Well, Terzaghi never lived long enough to see unsaturated soil mechanics developed, but if he would have, we could have run this little model for him this way. Taken those permeability functions, we put the water head on here. Here's the phreatic line that develops, and I've enlarged this part up here so you can see the water goes across the phreatic line, up over top, and then down the other side. Yes, the heads are dissipated across the clay core. They're also dissipated through the unsaturated soils. But it was this siphon effect, which is unusual. You can take virtually any unsaturated seepage computer code today, put in these properties, and it'll show you exactly this. The siphon effect is easy to understand. But it's these contrasting permeabilities that create this kind of a situation. Well, let me give you one more example. I said there are two ways we can have design our cross-section of the dam. Here's a dam now with a drain, a very coarse material in the middle. And then alongside it, we put a filter around the drain like this. And we put water against this dam. And now it dissipates through this material, and it's supposed to hit the drain and come out. But does it ever get to the drain? The water comes in, and it just touches the filter, and it runs down the filter, and it comes out horizontally here. The drain stays dry. You see, here's your phreatic line way down here. This is all negative water pressure. That coarse material is impervious. So no matter whether you try to put clay in the middle of your dam or you try to put gravel in the middle of your dam, you have got two contrasting permeabilities that are going to give us very unusual behavior. Our mind needs to learn to think the way the soil behaves. Now let's move towards some of the problems a little closer to home. Your home, Singapore. And we see these kinds of mass movements, and we say, oh, it's a surface slump. It's really not that important. But it is important to us. And we need to ask the question, can we do a better job? It is environmentally unsightly. It may have some risk as well. It's costly to repair. And there may be sustainable solutions that are possible. But those sustainable solutions don't just pop into our head while we sleep at night. There are steps that we need to go through to come to real solutions. Solutions require research. Solutions require an understanding of unsaturated soil behavior. And solutions require verification. So there are steps that we need to go through. The rainfall-induced landslide problem is common to many countries of the world. Very common in South America. Hong Kong has studied this problem for many years. It is a problem in which the moisture flux boundary condition creates the instability. The water table may be way down here, and you may have 20 meters of soil that is unsaturated. But under certain infiltration conditions, you can have instability. We are now bringing together two solutions. We must be able to model, first of all, characterize the moisture flux conditions on the surface. We must then model their seepage or their infiltration into the soil, and then combine the effects of seepage and slope stability to get our answer. We are having to do slope stability analysis that takes into account the shear strength of the unsaturated soils, the seepage that takes into account. In fact, the whole problem may be occurring within the unsaturated soil zone. So we looked someplace for solutions, and one of the obvious places to start to look is to the researchers who have been studying cover systems for mining operations. And I work with a company, Golder Associates, and pretty well a high percentage of our problems that we deal with are related to the mining operation, because every mining project has two streams of waste. It's got a coarse stream and it's got a fine stream, fines and coarse. And both of them must be protected from the environment. If you don't, the rain comes down, it hits the waste, it finds the pyrite in the waste usually, and comes out the bottom as acid rock drainage, which kills our fish, does a lot of damage to the environment. So the cover systems are very important to the mining industry. But most of their problems are wastes that cover square kilometers. They're flat. And so in your situation in Singapore, now all of a sudden we're saying, can we take those concepts and apply them to steep slopes? We ask ourselves, for these capillary barrier covers, have they come up with some design criteria? Yes, they have. They look at these permeability functions and say, where do they cross? Where do we want to be in terms of suction? And can we think of, if we change the coarse and the fine, can we create a situation where our contrasting permeabilities will work in our favor? Well, I'm not going to get into cover systems. I won't say anything more about them. But this is a study that was done at NTU. And so the thinking was done here. It says, can I, in my mind, create a plausible solution? I want to go through a series of slides because I want you to see that we don't wake up one morning and have all the answers, but there's a series of steps that we must go through because we are dealing with quite a complex problem. And so they decided, what about if we put in a fine layer over top of a coarse layer like this, and then put rain on it and study the effect of it? Well, yeah, we could build that, but what do we measure? How do we measure something that will tell us whether it's going to work or not under various rainfall conditions? So you go from the picture in your mind to building a model like this. And this model here is about 2 meters across, I believe, and it's got a fine layer over top of a coarse layer. And then you'll see they put in some instrumentation. There's two pieces of instrumentation that are very important here. Tensiometers, because they will measure the negative water pressure. Time domain reflectometry sensors, because they will measure the volumetric water content. Why is it so important to measure suction and water content? Well, remember the key piece to solving unsaturated soil problem was the soil water characteristic curve. Water content versus suction. They have these two variables. Now they can see, does the theory work? And so they took the sand materials and they would measure the drying curve. I'll just talk about the section 3, the drying curve, the blue here, and the wetting curve. So these are independently measured on the sand. Now with their instrumentation installed in the model, the 1G model in the lab, they start to put infiltration on the surface and watch as it wets up. Then they stop and they dry, and it comes down like this. It follows a hysteresis loop. It follows the drying curve, the limiting drying curve, and the limiting wetting curve. All three sections. What are they telling us? they're telling us that our theory is working for us. It appears we know the physics. We can solve it on our computer. We just have to come up with the ideas that will still perform properly for us under the imposed climatic conditions. Let me move along quickly. That isn't the end of it, just doing a test in the lab like that, although it's a very impressive test. They then went out into the field, picked a slope, and they're going to put the capillary barrier here. Why do we use this word capillary barrier? Because the water is going to come down through the fines and it won't go into the coarse, is the idea. Because remember, the coarse, it can have a low permeability. Water can't, that's why it's a capillary break there. So they're going to build this in the field. They're going to put in instrumentation below it to see if the suctions remain. Remember, it's the suctions that hold the slow up. It's the suctions that give you shear strength. And so this cover on the surface here is going to consist of, yes, some topsoil and grass, then some geocells filled with fine soil, a filter fabric in between, geocells with some coarse material, another drain, and then the underlying soil. So it's a complex system. It's time-consuming to construct. Over on the left-hand side, you'll see the coarse material has been laid down, filled in. Then here's the geofabric just over top of the coarse, and now on the right side here, they're going to fill in the fines. Let me give you a couple more pictures. This is with the coarse material being placed into the geocells. That's the coarse underlaying material. And then here's the filter fabric that's put over top, and now they're going to put on the fines, so it's a sandwiched type of construction. It's completed. We have a part of it without topsoil and grass and a part with topsoil and grass, which is going to perform better. And they measure all those suctions in the field, and this is an important line right across here, because this says you have suction in the soil. Above here, you do not. This is what's going to create the instability. But this is the original soil with no capillary barrier. Then when the capillary barrier system is installed, there's practically none that come above. There's a few over here, but now we have a lot more negative water pressures, a lot more strength. We look at this and we say, we are learning something. We're not saying we have a perfect system. We are learning something, and maybe we can do better. You see, this system that I just described to you has, if you put permeability of the soils here over suction here, you really have three: a coarse grain permeability function that goes like this. You have a fine grain that goes like this, and you have your residual soil like this. You have the interaction of three highly nonlinear permeability functions. I just use this point to illustrate that this is a complex problem. Our minds like to solve linear type solutions where everything is constant, but we don't have that luxury here. One more example, a test plot in the field just to test the effect of transpiration, the movement of water through plants. And so these are natural soils on this site, and then they put a test plot here and saying we like to have green on the surface, but we want to know, will it make it more stable? And so this is the test plots areas that were built. Now I'll just show you a summary graph that I took from their research work. And at the top up here it says, if you have the grass, you only get a drop in the factor of safety during this rainfall of 6.6%, but if you do not have the grass, you get a much greater drop. So transpiration, I haven't said much about it, but it also is an important factor. Now, as I conclude my talk, I want to leave you with a model in your minds a model to a question that I'm probably asked as any other question I've ever asked, and that is, can suctions be maintained in the soil? I hope you go away from here with this picture in your model. We have a ground surface, a water table, and if you covered the ground surface with asphalt or plastic or made it impervious, there would be no evaporation from that ground surface. It would be zero flux at the ground surface. If there's zero flux, it will come into equilibrium at a hydrostatic condition like this. So if you find this kind of an environment with an impervious surface at the top, and you tell me the water table is here, I will tell you what the suctions are above it. They will be like this. But now, remove the asphalt from the ground surface or the plastic from the ground surface and put on a moisture flux. How much? Here is the key to figuring out what's going to happen. You're going to have a ground surface moisture flux, and I want you to compare it to the saturated permeability at the ground surface. So this soil up here has a certain saturated permeability. You're going to put a flux on the surface. Let's put it on at about 50% of this saturated. If you put on a flux that's half of the saturated permeability, it will infiltrate under a gradient of 1, which means this line will be vertical. It'll come down till it hits this hydrostatic line and come over here. Now, it can rain at that rate 40 days and 40 nights. 40 years it can rain. And theoretically, it will never change from that line there. That's steady state conditions. Now, it might be hard to believe. But there's one other situation. You get some very heavy rainfalls. Let's look at one other case where we're going to increase the flux at the ground surface a little more. Now you increase it so that the flux is greater than the saturated permeability at the ground surface. Immediately when that happens, it will start to try to set up a new water table. It will go to 0 at the ground surface and it'll come down. And now your profile would look like this after a certain period of time. This is a transient seepage problem. Let it rain longer with the same rate. It comes down here and then like this and longer. So now the question becomes not, are you going to lose the suctions? Yes, you're going to lose the suctions. How deep are you going to lose the suctions? And how fast will you lose the suctions? So you ask yourself different questions for these two classes of problems. But these two examples here allow you to figure out, can suctions remain in the soil? I often have engineers try to explain to me that when it rains, you get a wetting front that moves down through the soil and all the suctions are wiped out. Therefore, why worry about suction? The suctions are only wiped out if that rainfall at the surface is greater than the saturated permeability. Now, just extend your thinking a little. What if I put a clay on the surface? All of a sudden, its saturated permeability is very low. Water can't get in, but clay's crack. But we can go through various kinds of scenarios. Let me summarize what I feel, and what I have already seen the government in Singapore here doing some very significant things. And I put it this way: HDB has shown it is possible to build an environmentally friendly and sustainable environment. HDB needs to be commended for their international leadership in protecting the environment and providing sustainable solutions through the use of unsaturated soil mechanics. Thank you for believing in unsaturated soil mechanics. HDB has in the process contributed significantly to engineering solutions involving unsaturated soil mechanics. And not only your problems in Singapore, you're having an effect internationally. Now, I pulled this picture from a magazine that I came across. And here's what struck me. I don't want to pass judgment on it, but this was referred to as the solution. And I looked at this and I said to myself, has it been studied? Has it been tested? Has it been verified from a theoretical and modeling standpoint? Or is it an idea? You dreamt up something. I want to just make the point that to come to solutions that you can use reliably over and over again, they can't only be an idea. They must be tested in the lab and in the field. The future. Researchers and practicing geotechnical engineers need to have a vision for innovation that can be used for engineering applications involving unsaturated soils. A vision for innovation. Not everybody can see where we should go next in order to find a solution. We may like this word innovation and say, yes, we want to be innovative, but it also costs. It costs money to be innovative. We also, researchers and practicing geotechnical engineers, need to have a will to implement the innovation. There are places where they don't want to use new ideas because they're fearful maybe they won't work, and so they do nothing. We need to have a will to implement innovation for near ground surface problems. Sustainability and environmental protection are intimately connected to the application of unsaturated soil mechanics. Thank you.